Welcome to the Deep Dive. Today we're plunging into something truly spectacular, powerful, and maybe a bit mysterious. Lightning.
Yeah, we've gathered quite a bit of material, some really detailed scientific explanations, the physics behind it all, but also looking at how we talk about it, how it shows up in culture.
Right. And our mission here is basically to unpack it for you. What is lightning, really? How does it work? What are its effects? Some are pretty surprising, and yeah, we're definitely going to tackle that old saying everyone knows.
The goal is for you to come away feeling, well, genuinely clued in about these incredible sky-high electrical shows.
Absolutely. And speaking of incredible, let's just start with the raw power. We're talking temperatures in that lightning channel. What, up to 30,000 degrees Celsius?
Uh-huh. Hotter than the surface of the sun. It's staggering.
It's unbelievable.
And the energy release? It can be anywhere from, say, 200 megajoules, maybe up to 7 gigajoules in a single flash. That massive, rapid energy release is what gives you the blinding flash and, of course, the thunder that follows.
It's awe-inspiring, maybe a little terrifying, too.
Definitely has that primal feel to it.
Okay, so how does nature even cook up that kind of power? Let's get into the anatomy of a flash. At its core, what is lightning?
Fundamentally, it's a natural electrostatic discharge. Think of it like a massive spark jumping the gap between areas with different electrical charges.
Like static electricity on a giant scale.
Sort of, yeah. But these charge differences can build up within a single cloud, or between two different clouds, or the one we notice most, between a cloud and the ground. The discharge is just nature trying to balance the books, electrically speaking.
And we see different kinds, depending on where that spark happens.
Exactly. The sources talk about three main types. There's intracloud, or icy lightning. That stays entirely inside one cloud. It's actually the most common type globally, believe it or not.
Really? More common than cloud to ground?
Yeah, significantly. Then you have cloud to cloud, CC, which is between two separate clouds. And then cloud to ground, CG, that's the one hitting the Earth, the one we study the most and are usually most worried about.
I feel like I've heard of others too, like heat lightning or bolts from the blue.
Right. Those are variations or related things. You can get lightning in volcanic plumes. Heat lightning isn't actually a separate type. It's just regular lightning from a storm that's too far away for you to hear the thunder. You only see the light reflected. Then there's dry lightning, which is a big fire starter because the rain evaporates before hitting the ground. Ball lightning is that really rare, weird, floating ball of light people sometimes report. Still pretty mysterious. And bolts from the blue? Those are fascinating. They can shoot out from the top, the anvil of a thundercloud, travel horizontally through clear air, and then strike the ground miles away. Often positive strikes, and can be quite powerful.
Wow. Okay, so lightning is the discharge. But how do clouds get charged up like that in the first place? That seems like the crucial step.
It absolutely is. It all comes down to charge separation, and this happens most intensely in the main updraft of the thunderstorm. We're talking about a region where the temperature is between about minus 15 and minus 25 Celsius.
So below freezing, what's going on there?
You've got this mix of supercooled water, liquid water below freezing tiny ice crystals, and something called graupel, which is like soft hail or snow pellets.
And they're all just swirling around, bumping into each other?
Exactly.
Yeah.
In that turbulent environment, they collide. And when they collide, charge gets transferred. The general idea, through what's called the non-inductive charging mechanism, is that the smaller, lighter ice crystals tend to pick up a positive charge.
Okay.
And because they're light, the updraft carries them way up high in the cloud. The heavier graupel particles tend to gain a negative charge.
And they stay lower down.
They either fall or get suspended lower in the cloud because they're heavier. So you end up with this separation, this layering of charge.
Like a giant battery in the sky.
Kind of, yeah. You get this tripolar structure typically, a big positive charge region at the top, a large negative charge region in the middle or lower part, and sometimes even a smaller positive area near the cloud base.
And the ground underneath reacts to all this.
It does. That big negative region in the cloud base induces an opposite positive charge on the surface of the Earth right below it. It's like an electrical shadow that follows the storm cloud as it moves.
So you've got positive way up, negative lower down, positive on the ground. That sounds like a recipe for tension.
Yeah.
An electric field.
Precisely. You get a very strong electric field building up in the air between these charged regions. The more charge accumulates, the stronger that field gets. Air is normally an insulator, but eventually the electrical pressure becomes too much for the air to handle. It breaks down.
And that's the discharge, the lightning.
That's the start of it, yeah. Let's focus on that cloud-to-ground strike, because it's the best understood. It doesn't just zap instantly. It starts with something called a leader.
A leader.
Yeah, it's a channel of ionized air that's been made electrically conductive that starts moving tentatively from the cloud towards the ground. For a typical negative strike, it's a negative leader coming down.
Is that the bit that looks like branches on a tree sometimes?
Often, yes. This leader doesn't usually go straight down. It proceeds in fairly discrete steps, maybe 50 meters or so at a time, pausing briefly between steps, and it often branches out, exploring different potential paths. That's the stepped leader.
Okay, so it's feeling its way down.
Pretty much.
Huh.
And as it gets closer to the ground, maybe within, say, 100 meters or so, that intense electric field it's creating is strongest on tall, pointy things on the ground, trees, buildings, poles.
And the ground responds. It reaches back up.
Exactly. These tall or pointed objects start launching their own little sparks of positive charge upwards. They're called upward streamers. They're trying to connect with the downward coming leader.
So it's like they're trying to meet in the middle?
That's a good way to put it. And when one of those upward streamers successfully connects with a branch of the downward stepped leader,
That's the moment.
that's the moment. It's called attachment. Suddenly, you have a complete conductive path, low resistance, all the way from the cloud charge region to the ground.
And then comes the big flash.
Yes. The main event, the return stroke. As soon as that path is complete, there's a massive surge of positive charge rushing up from the ground along that ionized channel. It happens incredibly fast, heats the air in that channel to, 30,000 degrees C almost instantly.
Wow, upwards. I always pictured it coming down.
The leader comes down, but the really bright flash, the return stroke, propagates upwards along the path the leader created.
But often lightning looks like it flickers, right? Like multiple flashes.
Good observation. That's because one lightning flash, the whole event you perceive, is often made up of multiple individual strokes. After the first big return stroke, the channel is still hot, still ionized for a fraction of a second.
So it could be reused.
Exactly. Another leader, called a dart leader, can zip down that pre-existing channel much faster without stepping and trigger another return stroke. You can get, typically 3 or 4 strokes in a single flash, sometimes many more, separated by milliseconds. That's what causes the flickering or strobing effect.
Okay, that makes sense. Now, you mentioned the damage isn't always from a direct hit. These currents can cause trouble, even if the lightning strikes nearby.
Oh, absolutely. When you have these huge currents changing incredibly rapidly, rising and falling in microseconds, they generate powerful electromagnetic pulses, EMPs.
Like in the movies.
Well, maybe not quite that dramatic usually, but the principle is similar. These pulses radiate outwards and can induce really strong, damaging currents in any conductors nearby. Think power lines, phone lines, network cables, metal pipes.
So even if your house isn't hit, your electronics could get fried.
Precisely. That's why surge protectors, SPDs or TVSS, are so important. They sit on your power lines and basically clamp down on those sudden voltage spikes, diverting the excess energy to ground before it reaches your sensitive equipment.
And there was something about the current traveling on the surface.
Yeah, the skin effect. At these high frequencies and rapid changes, the electrical current tends to concentrate on the outer surface or skin of a conductor rather than flowing uniformly through its whole cross-section. It's a factor in designing things like lightning rods to effectively carry the current around a building, not through it.
Wow, okay, so it's a really complex dance of physics happening up there.
Yeah.
And it's happening, well, all the time, everywhere.
It really is a global thing. The estimates are around 44 lightning flashes happening somewhere on Earth every second.
44 per second. That's hard to grasp.
Adds up to about 1.4 billion flashes a year. It's constant.
But not evenly distributed, you said.
Not at all. It's heavily skewed. About 70% of it happens over land, and especially in the tropics.
By tropics.
That's where you get the strongest convection. Intense solar heating, lots of moisture evaporating. It creates the perfect conditions for those really tall, powerful thunderstorm clouds, cumulonimbus clouds, to form.
And other things affect where it strikes more often, like mountains.
Yeah, definitely. Ground elevation matters, latitude is a big factor, prevailing winds, humidity levels, even how close an area is to oceans or large lakes, which act as moisture sources.
And it's mostly these huge cumulonimbus clouds that produce it.
Yes, those are the main lightning factories. Clouds with bases maybe only a kilometer or 2 off the ground, but whose tops can tower up to 15 kilometers, sometimes even higher.
Have there been any, record-breaking lightning strikes, longest distance or duration?
Oh, yeah. The World Meteorological Organization keeps track of these extremes. Back in 2020, they verified a mega flash over the southern U.S. It stretched horizontally for 768 kilometers.
768 kilometers. That's almost 500 miles.
Insane, right? A single flash covering that distance. And in the same year, down in Uruguay and Argentina, they recorded a single lightning event that lasted for 17.1 seconds.
17 seconds, just continuously flashing.
Essentially, yeah, the whole discharge process just kept going. And the speed of those leaders near the ground can be mind-blowing too, averaging something like 440,000 meters per second.
Just incredible speeds and scales. Does this happen on other planets? Like Mars or Jupiter?
People have looked. Venus has been debated, some controversy there. But more recently, we've actually detected definite lightning on Jupiter. Seems to be smaller flashes, maybe from shallower storms than the giant ones we usually associate with Jupiter, but it's there.
Lightning on Jupiter.
Cool.
Earth definitely seems to be the lightning capital of the solar system as far as we know, though.
Okay, let's shift focus a bit to the impact here on Earth. The power and punch, it's clearly not just a light show, it causes real damage.
Absolutely devastating potential. In nature, think about trees. The intense heat instantly vaporizes the sap inside. That creates steam, which expands explosively.
Splitting the tree apart.
Exactly. Can split huge trees right down the middle. It can heat trap water in rock crevices so fast it shatters the rock. It's a huge natural cause of wildfires, especially dry lightning, where there's no rain to put the fire out immediately.
And it can melt sand. I read about fulgurites. Yeah. Fulgurites are amazing. When lightning strikes sandy soil, the intense heat melts the silica sand along its path. As it cools, it forms these hollow, glassy tubes, basically fossilized lightning channels, like a snapshot of the strike's path underground.
Wow. And what about our stuff? Buildings, infrastructure?
Big problem there, too. Lightning wants the easiest path to ground, and if that path is through your house, well, it can cause structural damage, start fires, obviously fry any electronics it hits directly. And then there are those induced surges we talked about.
Right, the EMP effect.
Yeah.
Yeah.
That's why we have lightning rods, properly called lightning protection systems, on tall buildings. They're designed to provide a safe, intended path for the lightning current to travel around the building and into the ground rather than through it. And surge protectors inside handle the secondary effects on wiring.
So the rods don't attract lightning, they just give it a safe route if it strikes anyway.
That's the idea, yeah. They intercept a strike that was likely going to happen in that vicinity anyway and channel it safely. And remember, lightning can also follow conductive paths into a building, power lines, phone lines, even metal pipes if they offer a route to ground.
What about airplanes? They must get hit sometime.
They do, quite often actually. But modern planes, especially with metal fuselages, act like Faraday cages.
Faraday cages?
Yeah, it's a conducting enclosure that blocks external electric fields. So the lightning current tends to flow along the outer skin of the aircraft and exit off another point, usually leaving the people and systems inside unharmed. It can be startling, maybe cause some minor exterior damage like pitting, but it's generally safe.
That's reassuring. What are the main risks then?
Well, there's a small theoretical risk of fuel vapor ignition, though systems are designed to prevent that. Pilots can experience temporary flash blindness, which isn't ideal, and the strong magnetic fields can sometimes mess with magnetic compasses for a bit.
And the danger to people on the ground, it's often fatal, right?
It can be, yes. But it's worth noting that something like 90% of people who are struck by lightning actually survive.
90%. That's higher than I would have guessed.
It is, but survival often comes with severe life-altering injuries. We're talking serious damage to the nervous system, internal organs, burns, cognitive issues. It's incredibly traumatic for the body.
Okay, so that immense heat creates the flash, and that same heat creates the thunder.
Exactly right. That lightning channel, heated to 30,000 degrees in a tiny fraction of a second, causes the air right around it to expand explosively, violently. That rapid expansion creates a shock wave that travels outwards through the air.
And the shock wave is the thunder we hear.
Yep, the sound wave produced by that super rapid expansion.
Why does it often rumble then, instead of just being one loud bang?
Good question. It's because the lightning channel isn't just a point source. It's long, potentially kilometers long, and it might be branched. Sound waves from different parts of that long channel reach your ears at slightly different times.
Ah, so the sound from the closer parts arrives first, and the sound from farther parts arrives later.
Precisely. Plus, you get echoes and refraction as the sound travels. All that combines to stretch the sound out into that characteristic rumble or rolling noise.
And the old trick for telling distance. counting seconds between flash and thunder.
Still works. Light is basically instantaneous over terrestrial distances. Sound is much slower, around 343 meters per second, or roughly a kilometer every 3 seconds, a mile every 5 seconds.
So you see the flash, start counting.
And when you hear the thunder, stop counting. Divide the seconds by 3 for kilometers, or 5 for miles. Gives you a pretty decent estimate of how far away the strike was.
And if you see lightning, but hear nothing,
That's probably heat lightning. It just means the storm is too far away, generally more than about 20 miles or 32 kilometers for the sound to reach you effectively. Or it could be lightning high up inside a cloud where the sound is muffled.
okay. Now, lightning isn't just visible light and sound. It emits other things too. Radio waves.
Oh, yeah. Big time. Lightning is a powerful source of radio frequency energy across a wide spectrum. You can detect the radio waves from lightning strikes thousands of kilometers away. It's actually used in some lightning detection systems.
But then it gets even weirder. X-rays. Gamma rays.
This is where it gets really mind-blowing, yes. We've discovered that lightning produces bursts of X-rays and even incredibly energetic bursts of gamma radiation called terrestrial gamma ray flashes, or TGFs. These are some of the highest energy natural phenomena on Earth.
Gamma rays.
Yeah.
From a thunderstorm. How?
It's related to strong electric fields accelerating electrons to near light speed within the storm clouds, but the exact mechanisms are still being intensely researched. It's complex stuff.
Now I have to ask, the sources mention antimatter. Seriously.
Seriously, it sounds like science fiction, but it's real. When those high-energy gamma rays from TGFs interact with air molecules, they can actually produce pairs of electrons and their antimatter counterparts, positrons. We've detected the signature of positron annihilation coming from thunderstorms.
So lightning is creating antimatter above our heads.
In tiny amounts, yes. It was a completely unexpected discovery and shows just how much extreme physics is going on inside these storms that we're still figuring out.
That is just, wow. Okay, beyond the immediate flash, bang, and radiation, does lightning cause longer-term environmental changes?
It certainly does. One big area is atmospheric chemistry. Remember that intense heat. It breaks apart the normally stable nitrogen N2 and oxygen O2 molecules in the air.
And they reform as something else.
Yes, they can recombine to form various oxides of nitrogen, collectively called NOx. Lightning is a major natural source of NOx in the atmosphere. Estimates suggest it might increase the total amount of NOx by up to 90% globally compared to other sources.
Wow, and what does adding all that NOx do?
It has complex effects. NOx is a key ingredient in the formation of ground-level ozone or tropospheric ozone. That type of ozone is a pollutant and a greenhouse gas, contributing to warming.
Okay, so lightning leads to warming.
Well, it's not quite that simple. NOx also leads to the formation of hydroxyl radicals, OH, which are like atmospheric detergents. They help break down other potent greenhouse gases, especially methane.
Ah, so it helps remove methane, which is a cooling effect.
Exactly. So you've got this push and pull, creating ozone, warming, helping destroy methane, cooling. The net effect on climate is something scientists are actively trying to pin down with complex models. It depends on where the NOx is produced, how long it lasts, and many other factors.
Complicated. Is there a clearer effect on the ground?
Yes, ground fertilization. That NOx created by lightning eventually gets converted into nitrates in the atmosphere. These nitrates dissolve in rain and fall to the ground.
Like fertilizer.
Exactly like natural fertilizer.
Mm-hmm.
It's a significant way that nitrogen, which plants need to grow but can't use directly from the air, gets converted into a usable form and deposited onto land and into oceans, boosting plant growth. It's a key part of the global nitrogen cycle.
So lightning helps feed the planet, in a way.
In a very real way, yes.
Yeah. What about those strong magnetic fields? You mentioned EMPs. Did they leave any lasting trace?
They can, yes. The intense, rapidly changing currents in a lightning strike generate powerful magnetic fields. If the strike passes through rock or soil containing magnetic minerals or even metal objects, these fields can be strong enough to permanently magnetize them.
Like creating natural magnets.
Precisely. It's called lightning-induced remnant magnetism, or LIRM. It's even been proposed as a possible explanation for how some naturally magnetic rocks, like lodestones, originally formed.
Can scientists use that?
They can. After a lightning strike, you can map the magnetic anomalies left in the ground. The pattern and strength of this remnant magnetism can actually be used to estimate things like the peak current of the lightning strike that caused it.
That's clever. Now, there was one more really strange potential effect mentioned. Magnetic hallucinations. What's that about?
Yeah, that's a more speculative but intriguing idea. It stems from research into how strong, rapidly changing magnetic fields can affect the brain, like with transcranial magnetic stimulation, TMS. The theory is that the extremely powerful magnetic fields generated near a very severe lightning strike might, just might, be intense enough to induce temporary perceptual anomalies or even hallucinations in people very close by, say, within a couple hundred meters.
Seriously, lightning could make you see things.
It's a hypothesis, still under investigation. But it hints that lightning's effects might extend into realms we don't fully grasp yet, potentially interacting with biological systems in unexpected ways.
Adds another layer of awe and mystery, doesn't it? So how do we even track all this activity? 44 flashes a second globally. How is it detected?
We have pretty sophisticated systems now. There are extensive ground-based networks, especially across continents like North America and Europe. These use multiple antennas that detect the radio waves produced by lightning. By comparing the arrival times of the signals at different antennas, they can triangulate the location and estimate the strength of each strike very accurately.
And what about over the oceans or remote areas?
That's where satellites come in. There are instruments in orbit now, like the Lightning Imaging Sensor, LIS, or the Geostationary Lightning Mapper, GLM, that are essentially specialized cameras constantly watching the Earth for the optical flash of lightning. They provide near real-time mapping of lightning activity across almost the entire globe.
So we have a pretty good eye in the sky and on the ground. Can we trigger lightning on purpose?
Yes, it can be done primarily for research purposes. The classic method involved launching small rockets trailing thin wires up into active thunderclouds. The wire provides a conductive path, essentially telling the lightning where to strike.
Pulling lightning down with a wire sounds dangerous.
It definitely requires careful procedures. More recently, there's been exciting research using high-power lasers. The idea is to shoot an intense laser beam up into the cloud. The laser ionizes the air along its path, creating a kind of temporary conductive channel that can potentially trigger or even guide a lightning discharge.
Using lasers to control lightning. Wow. Okay, let's connect this back to some really big global issues. Climate change, air pollution, wildfires. How does lightning fit into that picture?
It's all interconnected, and honestly, modeling exactly how lightning will respond to climate change and how those changes will feed back is still a major scientific challenge. Cloud processes are incredibly complex to simulate accurately in global models.
What are some of the things scientists are seeing or predicting?
Well, regarding climate change, some models suggest shifts in lightning patterns. For example, maybe a slight increase in total lightning over parts of Africa, but perhaps concentrated into fewer, more intense storm days. A more consistent finding, though, both in observations and models, seems to be an increase in lightning frequency in the Arctic.
More lightning way up north. Why is that significant?
Because lightning has historically been quite rare in the Arctic. An increase there is seen as a sensitive indicator of warming temperatures and changing atmospheric conditions in that region. More instability, taller storm clouds, reaching colder altitudes where charge separation happens.
And air pollution. Does that affect lightning?
It seems to, yes. Aerosols, tiny particles from pollution like soot or sulfates, can act as cloud condensation nuclei and influence ice formation in clouds. Up to a point, adding more aerosols seems to actually increase lightning activity, possibly by affecting the sizes and types of particles involved in charge separation.
So pollution can make more lightning.
Up to a threshold, yes. But if the pollution becomes extremely heavy, some studies suggest it might actually suppress lightning, maybe by creating too many small cloud droplets that are less efficient at charging. It's a nonlinear effect.
And we talked about the NOx production from lightning, that chemical feedback loop.
Right. That's a key climate connection. Lightning makes NOx. NOx influences ozone warming and methane lifetime cooling. Yeah. The overall net climate feedback from changing lightning patterns is still uncertain and depends a lot on the specifics of the climate models used.
And the link to wildfires seems pretty direct.
Very direct. Lightning is a primary natural ignition source for wildfires, globally responsible for maybe 10% of ignitions overall, but much higher percentages in certain ecosystems like boreal forests.
And if climate change leads to more lightning, especially in places like the Arctic,
you get a potential positive feedback loop. Warmer conditions might lead to more lightning in sensitive regions like the Arctic and boreal forests. More lightning means more potential fire ignitions, More fires release more carbon into the atmosphere, contributing further to warming, which could lead to even more lightning.
A potentially dangerous cycle.
It's definitely a concern, particularly for those high-latitude ecosystems which store vast amounts of carbon. Increased fire frequency there could have significant climate implications.
It's incredible how this fleeting electrical discharge connects to these huge long-term planetary processes.
It really underscores how interconnected Earth's systems are.
Okay, let's bring it down to a more human level for a moment. How lightning exists in our minds, in culture. It's such a potent symbol.
Absolutely. Across cultures, across history, it shows up in mythology, religion, often wielded by powerful gods representing divine power, sudden change, destruction, or even creation. It taps into something deep.
And then there's that phrase everyone knows, lightning never strikes the same place twice. We use it all the time.
Yeah.
What's the cultural meaning there?
Usually when people say that, they mean that some unlikely event, especially a bad one, isn't going to happen again to the same person or in the same spot. It's meant to be reassuring, like, okay, you had your bad luck, it won't happen again.
Right.
It implies randomness and rarity.
Right. So that's the idiom. But is it literally true? Does lightning avoid places it's already hit?
No, absolutely not. Scientifically, it's completely false, a total myth.
Really? So it does strike the same place twice?
Oh, frequently. Lightning isn't random in that sense. It's always seeking the path of least resistance between the cloud and the ground, and what usually offers the easiest path.
Tall things, conductive things.
Exactly. Tall buildings, radio towers, prominent trees on hilltops. These objects get struck repeatedly because they consistently offer a better connection point for the lightning discharge.
You mentioned the Empire State Building earlier.
Perfect example. Gets hit something like 23 times a year, on average. Clearly, lightning has no problem striking the same place over and over and over again if it's a favorable target.
So myth thoroughly busted. It's funny how we use that phrase to imply randomness when the physics actually makes repeat strikes quite likely for certain spots.
It is ironic, isn't it? And I found that detail interesting, too, about French and Italian.
Oh yeah. Love at first sight translates literally as lightning strike, coup de foudre or colpo di fulmine.
It just shows how universally that image of a sudden, powerful, unignorable event resonates, whether it's falling in love or a massive electrical discharge from the sky.
So wrapping this all up,
Yeah.
what a journey. We've gone from tiny ice particles colliding miles up to charge separation, step leaders, return strokes hotter than the sun.
But we've seen how it spans the globe constantly. Its power to shape landscapes, start fires, create natural fertilizer, even generate antimatter.
Right, and how it influences atmospheric chemistry, potentially feeds back into climate change, and how it lives in our language, even in debunk myths. You've really gotten a deep understanding now of this everyday yet utterly extraordinary phenomenon.
And it makes you think, doesn't it? When you consider its power to forge magnets deep in the earth, to alter the air we breathe, maybe even to tweak our perceptions, what other powerful, unseen forces might be operating all around us, shaping our world in ways we barely comprehend, just waiting for a little curiosity to illuminate them?